We're still working with the very important UDU Mulberry section method this video, but the only difference is this is nothing but trig examples there. It's my experience that we tend to get those normal type problems a little bit quicker, and then we struggle with some of the trig integrals and the trig derivatives right there. So I just want to stress the tendencies again, all right? So these are for like the normal type problems there. Now, tendencies for choosing U, I'm just going to tell you what the tendencies are for a trig problem, and then we'll apply that to our examples there. So a lot of the times, like I said, this isn't something that works every single time, but most of the time, if you stick with these normal tendencies, you're going to be just fine here. So a lot of times we'll have a weird angle. And so I'll let my U equal the weird angle. And by a weird angle, I mean anything other than X. Like if I have a 4X in there, maybe let the U equal the 4X, and then that way I get a single letter in there instead of a weird angle there, right? And then the other stipulation is what I want you to remember is like, we'll let U equal a single power of a trig function. Which means if I have a cosecant to the fourth in the problem, I'm almost never going to let that equal cosecant to the fourth. I'm going to let it equal a cosecant, all right? Just a single power of that trig function right there. If you let it equal the stuff to the power, you're going to run into issues with that. So a single power of the trig function or the weird angle, that's typically what we have to choose from. Now, I just want to stress the importance of knowing your trig derivatives, all right? From our derivative chapter, you got to make sure you know the trig derivatives. You can't be doing these problems unless you know those trig derivatives like the back of your hand. So study those first. If you know the trig derivatives, I'm telling you the problems are easy. And the problems themselves pretty much tell you how to solve themselves, because you'll see these derivatives like for the squiggle part taking shape right there. So we know the trig derivatives, and then I want to review the trig integrals that we already know how to do. All right, so if you see these patterns right here, we already know how to integrate those. But what we're going to learn is like if I have like a secant of 4x tangent of 4x, how does that affect my answer? All right, so it's not just going to be secant of 4x plus c there. We got to be careful with that angle, and we got to make sure we're balancing things right there. So we'll show you with the basic ones how to handle with the weird angle, and then we'll show you some of the other ones where you need to change more than just that weird angle right there. All right, so let's go through. Got, I think, 6 examples I want to kind of walk through with you there. So the cosine of 4x, if I had a single letter right there, I could integrate that, right? If I had a cosecant of x, I know I can integrate that, make that sine of x. So really the only problem with this is I don't have a single letter right there. So that's your problem area. And so again, if we're working with our tendencies, I'm gonna stick with this first one. I'm gonna let U equal that weird angle right there. So I'm gonna let U equal the 4x. And then you're still going to do your same steps that we did before. So once we get U equals something, you're going to find the du, and you're going to write your integrals with the u's, and you're going to balance your numbers. Hopefully we have something we can integrate there. We'll integrate it, plug the x's back in, and remember the plus c. So we choose the u, and then we're going to find the derivative of that. So the derivative of 4x is just a 4, and we tag on that dx. And so that 4 is extra. I don't have like a 4 out here, so that 4 is extra. So we don't really have anything to squiggle other than like the dx if you wanted to squiggle that, but that 4 is extra. You're going to balance that 4 with a 1/4. And instead of writing the cosine of 4x, the 4x is equivalent to u. So you're going to write the cosine of u, and then we'll tag on the du. Eventually we'll do so many of those. There'll be a time where I loosen the reins and let us do some of these easier ones without as much work there. But right now we got to make sure we get plenty of experience underneath our belt before we can start taking any sort of shortcuts and doing some certain things in our head right there. So let's just make sure we show our work for that. And now we have something we can integrate, right? That's just from your list. You know, when you integrate cosine of a single letter, you're going to get the sine of that single letter. And then so that's what you're going to do. You're going to integrate cosine of u. That's going to give you sine of u. And then that 1/4 will carry down. Now, technically, I integrated. I can put my plus c right there. But I really don't need that plus c until like I'm done with the problem there when I plug the x's back in. And now all you got to do, plug your 4x, plug your x's back into your problem. And then remember your plus c, and then you're done. Now remember when we take the derivative of this thing, right? If I take the derivative of that, the constant would carry down, and the derivative of sine is going to be cosine of that angle, leave that angle alone, but then I would times it by the derivative of that angle, so I would times that by 4. Those 4's cancel out, and notice when we take the derivative of that, we should get what we started with on the inside of that integral right there, which I do. So you don't have to check that every single time, but it's available to you if you wanted to. All right, so as I look at this problem, as I'm trying to decide what to let u equal on this one, before I let u equal secant or let u equal tangent, I'm looking at that. I'm pretending, like here, I'm pretending if that's a single letter, I can integrate that. So I let the u equal that weird angle. If this weird angle was a single letter, if that was like secant of x, tangent of x, I asked myself, can I integrate that? And if you know your list like you're supposed to, and you're brushing those teeth, I can integrate. If I have secant tangent, I know I can integrate that, okay? So that problem then is that weird angle. So if I could just imagine if that's a single letter right there and I can integrate that, that's your problem, is your weird angle. And that's what tells me to let my u equal that weird angle, because then I'm going to replace those with u's and then I'll be able to integrate that easily. So remember what this is. So we let the u equal the weird angle, and then we do the du's. The derivative of 5x is 5, derivative of 4x is 4. So the derivative of 1 over 7x is just 1 over 7. And then we'll tag on the dx. And then that's an extra 1 over 7 that I don't have out here. So we're going to balance that with the reciprocal, which is going to be a 7 over 1. And the u is equal to those weird angles. So I rewrite the integral in terms of u, and I just replace those weird angles with that single letter. That was the whole point, to turn this into something easy that I can actually integrate. And then we're supposed to know we can integrate that. The integral of secant tangent is just secant. And now I have that extra 7 carried down. When I integrate secant u tangent of u, that gives me secant of u. And then because a derivative of secant is secant tangent, and then you plug your x's back into the problem. That u is equal to the x over 7. You tag on your plus c, then you're done. So there's 2 examples where we let u equal the weird angle. As I look at these next 2 examples, I already have a thing. You're never going to let u equal x. All you're going to do is switch that x to u's, and you're going to have literally the same exact problem. So you're never going to let your u equal just the x. On this one, if you're wondering, hey, do I let the u equal the 2x, let u equal the weird angle? I'm not telling you to always let u equal the weird angle. I'm saying that's one of the normal things that you're going to try, all right? And if that's not going to be the thing you try, it's going to be this other one where you let it equal a single power of the trig function. So the reason, I know I'm not letting u equal the angle here because I don't have a weird angle, and we're never going to let u equal the x. I'm not going to let the u equal the weird angle here because I'm imagining if that was a single letter, if I had cotangent to the 4th of x, cosecant squared of x, I can't integrate that. Like here, if I'm imagining those are a single letters and I get secant tangent, that's on my list of something I can integrate. But if I have single letters right here, the cotangent to the 4th cosecant squared, I don't have over here cotangent to the 4th cosecant squared. That's not on my list of things that I can integrate. So that tells me I have bigger problems than just that weird angle. So I'm not going to let the u equal the weird angle. I'm going to let u equal a single power of that trig function right there. Now, I'm going to choose wrong for the u on this one, just to show you what you run into. If I let u equal cosine of x on this problem, and I do the derivative of that, the derivative of cosine is a negative sign, and that's not giving me like a 1 over sine of x to the 4th. Okay, that's not giving me 1 over sine to the 4th x there. That's not matching up, right? There's nothing really matching up naturally right there. So that's why I'm not going to let u equal that. If I let u equal the entire power, right? That's going against the normal tendency. And usually if you do that, you're not listening to me and you're going to create issues for yourself. If I let u equal that whole sine to the 4th x, that's really sine of x to the 4th. And look what issues you run into with that. You got all this extra stuff that you don't need to worry about. Look, when you take the derivative of that, you're going to multiply by the power. You're going to leave the inside alone, decrease the power by 1. Then you're going to times it by the derivative of the inside. Now, when you look at this du and you're trying to match stuff up, it is true. You do get this cosine of x dx to match up. But see, you got an extra 4. That's not the issue. But you have an extra sine cubed x. You can't have extra variables. If you ever balance a variable, you can't balance out like a 1 over 4 sine of x cubed. So balancing numbers are okay, but if you ever try to balance an extra variable or an extra entire trig function and you put out in front of that 1 over 4 sine x cubed and you're trying to balance a letter, if you ever try to balance letters, I'm going to take out 10 points only if it's worth 7 points right there. It's a huge deduction, okay? So you can balance numbers with the reciprocal. If you have extra variables in the problem or extra trig functions in your du, you chose wrong for u. You can't do that, all right? So that's the issues that you run into. But I'm telling you, if you choose the normal tendencies that I gave you here, you're not going to run into those issues. So again, try normal stuff. There's so many times when I'm grading the first quiz over this or the first test with this, people just don't try normal things there. So a single power of the trig function. So here's what we're going to do. is I'm going to let you equal, oh, we already said the cosine didn't work, just a single power of the sine of x, not sine of x to the fourth, just a single power sine to the first. That's all I want. And when I let u equal sine, we do the du, the derivative sign is going to give us cosine. And then look, so you got your squiggles to match up, you got your squiggles to match up perfectly. There's no extra numbers that I need to balance. There's no extra variables that I need to worry about. That matches up perfectly. And so remember, the squiggled part is handled, and you're going to substitute for the rest of it. So since it's on the bottom, instead of 1 over sine to the fourth, your sine was equivalent to u. So now you have the easy integral 1 over u to the fourth, and then we tag on that du. So as long as you get that initial step down, it's very important when you're studying for this stuff. Study the first couple steps. What did the problem look like? What did you let u equal? Make sure you're getting that stuff down right, because once we get to this part, this is the easy part here. This is the integral of u to the -4. And then you're going to integrate that. Remember, you add 1 to that exponent. That becomes -3, not the -5. And you divide it by that same number. And that's going to be -1 over 3u to the third when you get rid of your negative exponents. And then you just have to plug your x's back in. So now I'm going to get my sine cube x, and I got my plus c, and then we're done there. All right, so on this one, if you let u equal a single power of the trig function, like I said, if I have single letters right there, I still don't get something easy like this where I can go straight to the integral. That's why I know I'm not letting u equal that weird angle. So my only option here is let it equal a single power of the trig function, which means my only option is to let u equal a cotangent of 2x or let u equal the cosecant of 2x. That's the only two things I want in your head right there. If you're trying anything weird stuff, you're not listening to me, you're not practicing as much as you should, right? If you let u equal a cosecant of 2x, if I say, what's the derivative of cosecant? You got to know that instantly. You must know your trig derivatives in order to get these right. Derivative of cosecant is a negative cosecant cotangent, right? So you'll get a negative cosecant of that angle, cotangent of that angle, leave that angle alone, times it by the derivative of that angle. Now, you could balance the extra number, but see, look, you're getting a cotangent of 2x. You're not getting that cotangent to the fourth of 2x. You're not getting that stuff to match up. It's not matching up properly. Don't choose that one. Your only other options is a single power of that other one. And so here's the thing. If you know your trig derivatives, if you know this list, these problems should be ridiculously easy to know what to let u equal at the beginning right here, because they're right there in front of your face. If I say, what's the derivative of cotangent? And you know the derivative of cotangent is a negative cosecant squared. Look at it. The derivative of cotangent is a negative cosecant squared. There's the squiggles part. You see, when you do that derivative, the squiggle part is right there in front of your face, okay? But each year, people try to do these without knowing those trig derivatives there, and you're going to be screwed, right? You have to know your trig derivatives there, and these are easy problems. So if I let u equal the cotangent, the single power of that trig function, when we take the derivative of cotangent, you're going to get negative cosecant squared that angle, leave that angle alone, and then you got to remember your chain rule times it by the derivative of that angle. We can tag on the dx like we always do, and then look at what we got there. So I got that cosecant squared 2x dx. I got that cosecant squared 2x dx. So when you do let it equal a single power of the trig function, if it has a weird angle, always just include that weird angle with it, because it'll be there in your derivative. It'll match up with the other part of the problem. And like I said, if you know the derivative of cotangent is negative cosecant squared, that's an easy problem right there, because you see that from a mile away, that squiggle, that derivative answer inside that problem right there. So that stuff is squiggled. That's good. All I have extra is just an extra number there. So we're going to balance that with the reciprocal. And remember, the squiggle stuff is handled. You substitute for the rest of it. U is equal to a single power of that. And so all you have is a u to the fourth du. And that's why we let it equal a single power, because if I have to integrate u to the fourth, that's not an issue. That's a very easy integral. So I don't have to handle that 4 over here at all and make that complicated on myself. I handle that 4 right here. So a single power of that. And then when you integrate this, you can get u to the fifth over 5. And then so you're going to get negative 1 over 10. And then you can plug your x's back in. So we're going to get cotangent to the fifth of that 2x. And then you got your plus c. Very simple, as long as you know those trig derivatives right there. All right, so same deal right here. Last two problems. This looks a little bit crazy, but it looks worse than it actually is there. I'm pretending if I had single letters right there, right? If you had cosecant of x, cotangent of x over square root of cosecant cubed of x, I can't integrate that. That pattern is not on my list of things that I can integrate. It's not like I see a cosecant square where I can go straight to the answer. That pattern is not on my list. And so my only other option, the tendency, is to let u equal a single power of that trig function right there. Also, this kind of merges with the first video where let's work with the inside of that square root, right? You know, another tendency was let it equal the inside of that square root, but not the whole inside, not the whole cosecant cube. Don't do that. Let it equal a single power of that. So what I'm going to try for is let it equal a cosecant of 4x, not the cube, just the inside of that, not really the inside of the square root, but it's going to that part, the inside part, but just doing the inside, just the single power of that. And so here's why you know you chose correctly just by looking at it. When you're ready, just by looking at this, you should know within a half of a second what to let the u equal. Because look, if you know your trig derivatives, if I say, what's the root of cosecant? And you spit out right away, negative cosecant cotangent, you see that stuff in the problem right away. So you just have to know your trig derivative. So we know the derivative of cosecant is a negative cosecant of that angle, cotangent of that angle. Leave that angle alone, and then you always times it by the derivative of that angle. The derivative of 4x is going to be a 4. And then look, boom, there's your squiggle stuff all matching up. And like I'm saying, you should know that right away, because when I look at that, I know the derivative of cosecant is negative cosecant cotangent, and then that's matching up right away. So that's why I know I'm choosing correctly there. And then if that's all matched up, you got an extra -4, so we'll balance that with the -1/4. And then again, the squiggle part is handled. You're going to go 1 over the square root. So we're going to go 1 over. We still have the square root there. And my u is equal to one of those cosecants, and you got it cubed. So it's going to be a 1 over u cubed. And then you tag on that du like we always do. And then now this is an easy integral. This is u to the 3/2 on the bottom. So 1 over u to the 3/2, that's u to the -3/2. And then we got to remember to integrate that. So when we integrate that, you add 1 to that exponent. So that's going to be u to the -1/2. We're going to divide it by -1/2, which means we're going to times it by a -2. This -1/4 will carry down. So this will give us a +1 over 2 square root of u. So I merged those, made that a 1/2, and I dropped that negative exponent down to the bottom. And then you can plug your x's back in. Your u is equal to a cosecant of 4x. And then you got your plus c, and then you're done. They look worse than they actually are, but I'm telling you, if you know those trig derivatives, you're going to be excellent at these, and just try the normal things. You're going to be good there. All right, last example here. The tangent squared is not on my list of things I can integrate, okay? So I don't have tangent. I got a secant squared there and a cosecant squared there. So that leads me to the importance of your Pythagorean identities. So I mentioned those in the first video. You could get those down right there. Those are our Pythagorean identities right there. So if I have a tangent squared in my problem, I can't integrate a tangent squared. But if I rewrite the tangent squared as a secant squared minus 1, the power of that is the secant squared is on my list of something that I can actually integrate right there. So there's 2 ways that I could do this problem. I'm going to actually show you both ways there, whichever way makes sense in your head. But when I see that, I know I can't integrate that. I'm right away going to use the Pythagorean identities and rewrite that as secant squared of 8x minus 1. And now I know I can integrate a secant squared, but what I'm going to do, so essentially this is secant squared of 8x dx minus the integral of 1 dx. And this right here is a u du problem, just like these up here. So the secant squared, I know that's on my list of something I can integrate. So my problem is that weird angle. So I'm going to let u equal to 8x, that weird angle. The du is equal to 8. So I'm going to balance that with the reciprocal, the 1 over 8. And now I have secant squared of u du. And then remember, when you integrate secant squared, that's going to be tangent, because the derivative of tangent is secant squared. And then I can plug the x's back in. And then so I'm done with that first part of it. And then this is the integral of 1. These differentials are important, because if that's the integral of 1 du, then that's a u right there. And I got to plug an 8x back in. But that's the integral of 1 dx, because I separated that. And I did this one minus the integral of this one. So when I integrate 1, that's just going to be minus x. And I tag on that plus c. And then we're done right there. Now, there is one other approach that sometimes students take on this that I just wanted to mention, so we're not making any common mistakes at all. But sometimes I see students do this. They'll let u equal the weird angle right away, and then they'll do the du is going to be an 8, and so they'll balance that with the 1 over 8, and then they get this tangent squared u du. All right, and then they realize that they can't integrate tangent squared. Then they realize they're going to plug in the Pythagorean identity and make that secant squared u minus 1, and then they got the du. And then so when you integrate secant squared, that's going to give you a tangent because the derivative tangent is secant squared. But see, now when you integrate the 1, this is a du. So when you integrate 1 with respect to u, that's a u. And then that 1 over 8 is out in front of that. So there I integrated it. And then when you plug your x's back in, your u is equal to the 8x. So we're looking at that. And then notice that if I distribute the 1/8, 1 over 8 times the 8x is the minus x, and then that plus c right there. Sometimes when students do that, though, they get, when they integrate this 1, they just put an x right there, and then they'll have like a 1/8 x or something like that. So there's just 2 different ways that you can kind of get that, whatever way it kind of works in your head. Sometimes you just might do something, you run into something in the middle. Just be a little bit careful with the dx's and the du's there, and just practice these as much as possible. I know I have that. I know I have my work for all the even answers in this section there. Very neat work there. It was very important to study the beginnings of those problems right there, what you can and cannot integrate, what your trig derivatives are, and trying those normal things and letting u equal the normal things, and we'll be good. But like I said, even if we're struggling with this at the beginning, this is something that's going to be easy for everybody. We just got to keep working at it, keep asking questions, and get as much practice with this on the front end of things. So we hope we get it down for the first time that we assess over and don't have to worry about it for the future there. All right, practice as much as possible. Let me know if you got questions. Thank you.